We have already seen and heard much about lines and quadratic functions. We now consider polynomial functions with higher degrees. First of all, a polynomial function is always a smooth and continuous function, much like the cubic function you see on the page before you. A polynomial function will never have any breaks or tears in the function's graph. Nor will a polynomial function have any sharp corners or edges. There are some features about the equations of polynomials which will lend themselves to helping us sketch them. Given any polynomial, if the degree of the polynomial, that is, the leading power, is odd, and the leading coefficient is positive, the graph of the polynomial will look much like the graph shown before you. The notation here says that f of x tends towards infinity as x tends towards infinity, and that f of x tends towards negative infinity as x tends towards negative infinity. You can read that as go up to the right and go down to the left. Here we have an example of, again, an odd degree, but the leading coefficient in this example is negative. In this case, the polynomial goes up to the left and down to the right. Once more, you read the notation, f of x tends towards negative infinity as x tends towards infinity as down to the right, and f of x tends towards infinity as x tends towards negative infinity as up to the left. Suppose that the degree of the polynomial is even and that the leading coefficient is positive. In this case, it goes up to the left and up to the right. If the degree is even and the leading coefficient is negative, then it goes down to the left and down to the right. No matter what the degree of the polynomial, a polynomial function has at most as many zeros as the degree. There are many ways to talk about what is the zero of a function. The zero is where it crosses the x-axis. It is a solution to the polynomial equation when you set the function equal to 0. It is also a factor of the polynomial if you write it as x minus a. And every zero is an x-intercept of the graph of f. In addition to having at most n zeros for a polynomial with degree n, a polynomial will also have at most n minus 1 possible extrema. That's referring to any minima or maxima of the function. Here's an example of a polynomial function that has two zeros. It has a 0 when x is equal to 2, and also a 0 when x is equal to 1. Notice that in the factored form of the polynomial, we have x minus 2 squared. We say that the 0 where there is a square or a cube has a multiplicity, so in this case, x equals 2 is a 0 with multiplicity of 2. Also, notice that the function only touches the x-axis when x is equal to 2, but it crosses the x-axis when x is equal to negative 1. Here we have another example of a polynomial with multiple zeros. We have a 0 of multiplicity 3 when x is equal to 2, a 0 of multiplicity 1 when x is equal to negative 1, and a 0 of multiplicity 2 when x is equal to negative 5. Once again, we see that in a couple of places it crosses the x-axis, in a couple of places it only touches the x-axis. It would appear that whenever the function has a multiplicity which is even, it only touches the x-axis at that point, but when the multiplicity is odd, it crosses the x-axis. It is in fact true in general that a polynomial with a 0 that has an even multiplicity touches the x-axis, and a 0 of odd multiplicity will cross the x-axis. We can use this to help us graph these polynomial functions. Suppose we pick any 2 points on the function. What do you notice about the values in between those 2 points? Here I've highlighted an example in red. Between the 2 points on the graph, there are many intermediate values. These are y values on the graph of the function. The intermediate value theorem states that for any continuous function, which a polynomial is a continuous function, the continuous function will touch every possible y value between the y values which the function achieves. More formally, and this is the precise mathematical definition, if you have two x values, a and b, such that a is less than b, if the function is continuous and the points at the end are not equal, that's kind of an important part, then in the interval f takes on every value between f of a and f of b. Now, this is a much more of a mouthful to say, but the meaning is the same. You pick 2 points on the function. Because it's continuous, it's impossible that the function doesn't take on every y value between those 2 points. So once again, if we look at this picture, between the 2 red dots, every possible y value is taken by the function. It doesn't jump, it doesn't skip, and there's no tears or holes in the graph. We'll be using all of these pieces, knowing what the end behavior of a polynomial function is, knowing whether a zero crosses or touches, and the fact that the intermediate value theorem is true in order to sketch polynomial functions of higher degrees.